previous lecture we developed a model for the transistor for FET. That model is applicable and will be used for the analysis of amplifiers which are constructed using either junction field effect transistors or MOSFETs. So, the analysis which we shall be currently carrying, that is applicable for MOSFET circuits as well as for JFET circuits. We will recall, let us recall that the bipolar transistor can be used in 3 configurations, and that gives common emitter circuit, common collector circuit and common base circuit. In the same way, a field effect transistor can be used in 3 configurations, and we have 3 kinds of amplifiers. Three types of amplifiers: the common source amplifier, that is CS, common source CS, like CE amplifier in BJT. So, similarly here common source CS amplifier. And then we have common drain, that is CD amplifiers. And then we have common gate, that is CG amplifiers. We will study all these 3 amplifier circuits, and by study we mean that we are going to derive expressions, analytical expressions for the characteristic parameters for the amplifier. And you will recall from our previous study that characteristic impedance for a amplifier, these are for example voltage gain, input impedance of the amplifier. These 2 are most important parameters for the which will decide the performance of the circuit, and then there are some other considerations like what is the output impedance, which is important in some cases. Now, out of these 3, common source amplifier in junction field effect transistors or in MOSFETs, this is most widely used. This is like common emitter circuit for BJT. In FETs and MOSFETs, the most commonly used, most widely used amplifier is the common source amplifier. Then we will study common drain amplifier, which is like that CC, common collector or emitter follower. This is known as source follower, and it has the similar application as the emitter follower for matching purposes. So, it is used as a buffer amplifier. And common gate amplifier is like common base amplifier, and this has very limited applications for the simple reason that the input impedance of common gate amplifier is very low. It is few hundred ohms only. So, it has limited applications. We go one by one for the study of these amplifiers. First we take common source amplifier. common source amplifier, which for example with a JFET can be drawn like this. This is the circuit. Here we connect the biasing source, the battery VDD, and this is RD, this is RS. You are familiar with these resistances, and this is RG, and this is the input signal V in. This is to be amplified, and the amplified signal is taken at the output here. This is the common source amplifier, and here the input is given between gate and source, and output is taken from drain and source. Now this is the coupling capacitor, and here this is C1 is coupling capacitor, and C2 is bypass capacitor. If we do not use this C2 bypass capacitor, then there will be drop, AC drop across this resistance, and hence the gain, the output voltage which is available, that will fall. This point we will discuss again little later. Now first we should draw AC equivalent circuit for this actual circuit. This is the actual common source amplifier circuit, which makes use of these three resistances, two capacitances, the input signal, and the output is taken here. And we draw the AC equivalent of that. For that, let us remind you, we have talked all these points when we talked about the analysis of a bipolar transistor amplifier analysis, but again briefly we talk about them. That for drawing AC equivalent, first thing is that DC voltage sources are grounded. DC voltage sources are grounded. Second point is that these coupling and bypass capacitors, they are taken as short at the frequency for which this circuit has been designed. We choose these capacitors such that the impedances offered by them at the frequency of interest are negligible, and hence they can be taken as short. So capacitors C1 and C2 are taken as short circuited. So keeping these points in mind, the equivalent AC equivalent circuit is this. This is the AC equivalent of circuit in figure 1. This is figure 1, this is figure 2. So, this is AC equivalent of circuit figure 1. Here once we take this as short, so this is shorted. Once we consider this bypass capacitor as short, so this resistance is shorted, so 0 resistance. So, this is like that, and this is grounded. So, this is like this, and output is taken against this resistor RD. This is the AC equivalent. Now, we will replace this transistor, this FET or MOSFET, whatever is, by its model. So, what we get is this. This is the gate terminal, this is the input V in, and this is the transistor in the circuit. In the AC model we have replaced by its AC equivalent circuit, we have replaced by the model, and this is drain. So, and this is the current source, which is equal to GM into V in, and here because this resistance is very high, so V in is equal to VGS. You will recall that this current source in the model we have taken as GM into VGS, but here we have shown it as GM V in because of this, and this is true because RG is very high. With this now we can draw, these resistances are in parallel. With this there may be additional resistance, for example a RL, the load resistance, or another stage which is connected in series with this amplifier. Then what will be the input impedance of this next stage that will be taken here. So, all these resistances are in parallel. So, actually this can be replaced by one resistance RD, and which is RDS in parallel with RD in parallel with RL. One thing which is very frequently used in this analysis at many places in electronic circuits, when two resistances, one high resistance, one low resistance, when they are connected in parallel, then the effective resistance of the combination is closer, in fact smaller than the smaller resistance. Take just one example, 100K resistance and 1K resistance, if they are connected in parallel, then what will be? You apply that parallel resistance rule and find out the effective value of the resistance. This will be lesser than 1K, but close to 1K. So, here this resistance is highest, which will have least effect on this. So, this will be very close to RD. So, this model, all these resistances we can replace by RD, where RD will be equal to this. Also RG is very high resistance. This we have seen 50K, 100K. So, this can also be dropped from this figure, and then this model becomes this. This is the model which we are going to use, and remember the current source is GM into V in. V in is the input voltage. Then the drain current ID, that is this current source, and see the direction. So, current is flowing ID, and this ID, the drain current in the circuit, and this is equal to GM into V in. And look at the direction of current here, this is this way, and the particular direction which we have taken for V out is just opposite. That is, current normally flows from higher potential to lower potential, but this is flowing this way, and hence it is in order to write V out equal to minus this resistance R d into I d. We substitute for I d from this equation. V out is minus GM R d V in, and from here the voltage gain A V is equal to V out, output voltage, AC output voltage divided by AC input voltage. So, V in, and this is equal to minus GM into R d. This negative sign simply says that there is a phase reversal in this amplifier, meaning when input will be maximum positive, this is varying signal, when input signal is maximum positive, the output will be maximum negative, and so on. That is the meaning of phase reversal. So, this sign simply indicates phase inversion or reversal, phase inversion. Like common emitter BJT amplifier, that also has a phase inversion. So, similarly it has phase inversion here, and the magnitude of voltage gain A V is simply GM into R d. Just to give an example, if GM is 4000 microsiemens, that is the unit in which GM is written, 4000 microsiemens, and let R d, that is all these resistances in the amplifier, the parallel combination of this, for example, gives R d to be equal to 4 kilo ohms. Then according to this relation, the voltage gain is 4 into 10 to power minus 3, that is GM into R d, which is 4K, 4 into 10 to power 3. So, voltage gain is simply 16. This is a simple expression which expresses the voltage gain of the amplifier. Now, in the circuit we have taken that RS is bypassed by the bypass capacitor C2. In certain circuits we don't bypass this resistance RS. In that case, as I said in the beginning, there will be a AC drop across this resistance also. So, the drop will fall, or in other words the gain will fall. For the same input, if this is not bypassed, we get lesser output because the gain will fall. So, in that case, if resistance RS is not bypassed, in that case this gain will be reduced, and this is equal to GM RD by 1 plus GM into RS here, and once we bypass it, then this RS becomes 0 and we return to this expression. So, this is about the voltage gain, and then the input impedance. Input impedance of the amplifier. Input impedance of the amplifier. We can see from, for example, from this model that input impedance, if we measure at the input terminals between gate and source, this will come out to be equal to Rg, and Rg is very high. So, input impedance Zi, this is equal to Rg, this is very high. Normally Rg will have range 100 coulombs to 1000 or more coulombs. So, input impedance is very high. So, we can summarize that CS amplifier it has high voltage gain, and very high input impedance, and it has a phase reversal. Phase inversion. These are the characteristics of a CS amplifier. One thing I may mention here, that voltage gain for MOSFET or junction field effect transistor, if we compare with a bipolar transistor, it is much less. But there are other benefits. So, FETs are very widely used, and this not very high input not very high gain, this can always be compensated by adding another stage, amplifying stage, which is not a problem at all. If two stages each having gain 10, for example, if two stages are cascaded, are connected in series, where individually each stage has a gain of 10, then the two stages will have a combined gain of 10 into 10, that means 100. So, this is no problem. Then we go for the next amplifier, that is common drain amplifier. Common drain amplifier. Let us first draw the circuit. This is the circuit. This is common drain amplifier circuit. Few features may be noted. One is that drain terminal is directly connected to the DC source. When we draw the AC equivalent, then this is to be grounded, as we have talked that AC equivalent circuits require that DC voltage sources have to be grounded. So, we ground it. So, that means that drain is at AC ground. This is one point. Second point is that output we are taking at the load connected at the source. So, the second point to be noted is that load is connected at source. So, the output that means output is taken from source with respect to ground. Here source with respect to ground. This is the only amplifier in which the load is connected at the source and output is drawn. Now, we will draw the equivalent of this. These are the coupling capacitors C1 and C2, and we draw the AC equivalent of this figure and of common drain amplifier, and this is the drain terminal at AC ground. This is the AC equivalent circuit. This is the input Vs, and this is G, this is Rg, and this is V in. This is Gm into Vgs, and then Rds RS and RL. This is the circuit. This is drain, this is source, and this we can, as we have done earlier, we can replace this resistance is Rg, of course. These three resistances are in parallel and that can be replaced by, say, RL. So, RL will be RDS in parallel with RS in parallel with RL, and normally this is very high resistance. So, this RL effectively will be very close to RS in parallel with RL. So, we can replace these all three resistances by this. And another interesting point is that the gate terminal with respect to ground, this is at V in. This is the gate at V1 with respect to ground, and source with respect to ground is at V out, and source is at V out with respect to ground. So, what will be VGS if gate with respect to ground is at V in and this is source is at V out, then VGS will be V in minus V out. VGS is equal to V in minus V out, and let us call this equation 1. Now, what will be V out? I can draw another circuit by just replacing these three resistances by 1. So, in that case it will be, this is RL and here this is RG, this is GM, VGS, and this is ID, this is plus minus V out, and from here we can write V out from the circuit. Obviously, this current when passes through this effective AC impedance RL, that will produce the output. So, ID into RL. Now, ID is equal to this. Since ID is equal to GM VGS, so we have V out equal to GM RL into VGS, and VGS from equation 1 we have this. So, we write like that, putting for VGS from equation 1, we have V out GM RL into V in minus V out, or V out 1 plus GM into RL equal to GM into RL into V in. From here we can write for the voltage gain. The mathematics is very simple, so simple that it is almost very straightforward. So, the voltage gain AV by definition is V out by V in, and this is equal to GM RL by 1 plus GM RL. One thing let me make clear, that here the signal is Vs, but here we are showing it as V in, because there is a small resistance here Rs, source resistance. So, sometimes there is a small drop across this resistance that makes Vs not exactly equal to Vgs. So, this is taken as Vs, and here this is going to the circuit V in, because there may be some impedance which is normally associated with the AC source at the input, and there may be some drop across this. So, that is why the two have been taken as different. Anyway, so this is the expression for the voltage gain. GM into RL normally is much higher than 1, that is AV we have obtained as GM RL 1 plus GM RL. Normally, usually GM into RL is very large as compared to 1. So, 1 can be dropped, then AV will be very close to unity. When AB is 1, that implies that there is no voltage gain. There is no voltage gain. It is whatever is the input, same appears at the output, but there will be some power gain. Now, so this is this. Now, here the input impedance we find out, gain we have seen. Similarly, for the emitter follower, the gain was close to 1, and as I said that this is used as a buffer between stages, and hence same is here. The input impedance, when we measure, because this resistance is normally very small as compared to Rg. So, it is the input impedance is high, Z in is equal to Rg and Rg is very high. Input impedance is very high, gain is 1, but let us see the output impedance. The output impedance. Look at this circuit. This was the common drain amplifier. Now here and its equivalent we draw here. Now as a rule, whenever output impedance is to be measured, then we disconnect RL. This is the general practice, and always this is done, that RL is to be taken out. Then what will be the impedance which we will get at the output, that means between source and drain, and this is simply these two resistances. This is the drain source resistance and this is the source resistance. So, the two in parallel. Therefore, the output impedance Z out, this is equal to R ds in parallel with Rs, and as I said, as a practice, RL is always removed, disconnected from the circuit to measure Z out. So, we are left with these two resistances in which this resistance is very high. So, Z out is very closely equal to Rs, and source resistance normally is kept low. Rs normally may be 200 or 400 ohms. Therefore, the output impedance only for this circuit is very low. Input impedance is very high, output impedance is low. So, this amplifier can be used to act as a buffer between very high impedance on one side and low impedance on the other side. Low impedance will match with the output impedance here, and the high input impedance will match at the other point. So, this is that. In summary of CD common drain amplifier, which is also known as source follower, here the gain is close to 1, but actually it is less than 1, and input impedance very high Rg, and output impedance Rs low, and it is used for buffer purposes. The last one is the common gate amplifier. The common gate amplifier, it is different from the earlier two which we have studied, the common source and common drain, and the reasons will be very clear. The input impedance here is extremely low. The circuit we can draw like this. just directly I have come to the AC equivalent by grounding it, because we have done it quite a few times. So, you understand this is the input signal, this is grounded, this is source, this is drain, and this is gate. This is the common gate. Gate is common between input and output. Output is taken between drain and ground, and this is the effective value of RL, which we have talked 2 times at least in the 2 circuits. Here the V out is ID into RL, and ID is GM into VGS, which is, and VGS is same. You can see this voltage here, VGS is same as V in. So, this we can write V out as equal to GM V in into RL, or the voltage gain AV is V out V in, and that is equal to GM into RL, which is high. And now we come to the input impedance. The input impedance. In this circuit, it is not difficult to realize that input current is the same as the current between drain and source, that is ID. If we see the circuit, when we discussed about this, how the current flows between drain and source, so it is not difficult at all to see that I in is equal to ID, and ID, if we replace this by the simple model, then ID will be equal to GM into VGS, and this is equal to VG in, GM into V in. Because gate source voltage is the same as this we just discussed this. Therefore, Z in is equal to V in by I in. This is I in, and this is simply equal to 1 by GM. GM, so this is very low input impedance, and let GM be equal to, as we have taken earlier, 4000 micro Siemens. Then Z in will be 1 by 4 into 10 to power minus 3. We have to put in Siemens. So, 4000 micro Siemens is 1 by that is 4 into 10 to power minus 3 Siemens, and this is equal to 250 ohms, very low impedance. The output impedance is high, the input impedance is low, and so this amplifier has limited applications, this is equivalent to common base amplifier in the BJT. So, this way we finish the analysis of the amplifying circuits. The most whenever we want to use the amplifying circuit using a MOSFET or a junction field effect transistor, then we make use of common source amplifier, and that common drain amplifier is used as a buffer whenever we have here one stage which is having high output impedance, high Z out, and then here this is some other device, some other circuit where this is having low impedance. They can't be connected together because of the mismatch. The most of the power will be reflected and very little will pass on to this circuit. So, we require a buffer here, and this common drain amplifier which has high impedance that will match with this, and low impedance here will match with this. So, this is the buffer amplifier, very widely used in these circuits. So, this was the analysis, and we have completed that. Next thing which we will be taking, which is very important as far as the circuits are concerned, many times the MOSFET circuits, particularly because in integrated circuits very widely used are the MOSFETs. So, MOSFETs or even junction field effect transistors, but that is normally reserved for discrete devices. So, MOSFETs can be connected as resistors, as capacitors. That means, whenever a resistance load is required, that instead of having a resistance there, we can use a properly connected MOSFET. When we connect a simple resistance, that is called, for example, this resistance, and here is a MOSFET. This resistance R D, for example, this is called passive resistance, passive load, and this consumes power, and when this resistance is replaced by an active device such as another MOSFET properly connected, then what we have? Active load. So, how to connect the MOSFETs as resistors and capacitors, this is we are going to take next.